Have you ever wondered how a train, a massive chunk of metal, moves without sliding off the tracks? This behemoth, often weighing several thousand tons, defies our basic understanding of balance and gravity, staying perfectly poised on narrow strips of steel. It's a question that sparks curiosity, inviting us into the captivating world of railway systems and the engineering miracles that make them work. So, buckle up, for we're about to embark on a thrilling journey to unravel the mystery behind this engineering marvel. The secret to a train's stability starts with the design of the tracks themselves. A train track, at first glance, might seem like a simple pair of parallel lines, but if you look closely, you'll find that there's a lot more to it than meets the eye. The most integral part of a train track's design is its unique V shape. This shape, also known as the track gauge, is defined by the distance between the inside faces of the load-bearing rails. The standard gauge for most of the world's railways is 4 feet, 8.5 inches, but why this odd dimension, you might wonder? Well, it's a historical standard set by the British, and it has proven to work well over the centuries. Now let's delve deeper into the V shape. The rails are not perfectly parallel but slightly angled. This subtle tilt is what helps the train stay on track, quite literally. The wheels of the train, which we'll discuss in more detail in the next scene, fit snugly into this V shape, creating a self-centering system. As the train moves, it naturally wants to go straight, and the V shape of the tracks helps to ensure that it does exactly that. Additionally, there's a little piece of metal on the inside of the rail called the flange. The flange, though small, plays a significant role in the train's stability. It acts as a guide for the wheels, preventing them from sliding off the rails. The flange and the V shape of the tracks work together to keep the train in its place. So, it's not just about laying down two pieces of metal and letting a train roll over them. There's a lot of thought, precision, and geometry involved in designing train tracks. The track's unique design, coupled with the clever use of the flange, creates a system that allows heavy trains to move at high speeds without the risk of derailment. So it's the unique design of the tracks that lays the foundation for a train's stability. Now that we understand the design of the tracks, let's move on to the wheels of a train. An interesting fact about train wheels is that they are not flat, but conical in shape. This unique design is not a coincidence, but a product of ingenious engineering. The slight angle of the train wheel, tapering to a point, is not just for aesthetics. It serves a crucial purpose in the smooth and efficient functioning of the train. When you picture a train moving along its tracks, you might imagine the wheels as perfectly round, but that's not the case. The train wheels are designed in a way that the diameter is larger on one side than the other. This difference in diameter is what gives the wheel its conical shape. So, why are train wheels conical? The answer lies in the principle of equilibrium. When a train is moving straight, the diameters of the wheel running on the inner and outer rails are the same. But when the train approaches a turn, the wheels need to cover different distances. The outer wheel has to travel further than the inner wheel. Here's where the conical shape comes into play. As the train turns, the conical shape of the wheel allows it to shift along the axle. The outer wheel, with its larger diameter, moves toward the larger end of the cone. Simultaneously, the inner wheel, with its smaller diameter, shifts toward the smaller end of the cone. This shifting allows the wheels to cover different distances while maintaining the balance of the train. The principle of equilibrium ensures that the train does not lean too much into the turn, which could cause it to derail. It also minimizes the friction between the wheels and the track, allowing the train to move smoothly and efficiently. This simple yet effective mechanism is a testament to the marvels of engineering. It's a perfect example of how a simple design can solve complex problems. These conical wheels, in harmony with the tracks, ensure the train stays on course. The genius behind this design lies in its simplicity and effectiveness, proving once again that sometimes the best solution is the simplest one. You might be wondering, how does this all come together? Well, it's all about physics. Let's dive right into the principles at play here. First off, we've got gravity. It's that invisible force that keeps us grounded and also helps keep our train snug on its tracks. But gravity alone isn't enough. That's where friction comes in. It's the resistance of motion when one object rubs against another. In our case, it's the steel wheels of a train rubbing against the steel tracks. Friction is a crucial player because it provides the gripping force that allows a train to move forward without slipping. Now you might be thinking, if friction is so great, why don't we have more of it? Well, too much friction isn't a good thing either. It can cause excessive wear and tear on the wheels and tracks and even slow down the train. So we need just the right amount of friction. Not too much, not too little. Next up, we have the centrifugal force. It's the force that makes you feel like you're being pushed outward when you're spinning around in a circle. When a train takes a turn, it's the centrifugal force that wants to push it off the tracks. But don't worry, our train isn't going anywhere, thanks to the conical shape of the wheels and the tilt of the tracks that counteract this force. So we see that gravity, friction, and centrifugal force are all working together in harmony, each playing their part to keep our train on track. But let's not forget about the train's speed. It's carefully controlled to ensure that these forces remain balanced. Too fast, and the centrifugal force might get the upper hand. Too slow and friction might drag us down. And there you have it. It's a delicate dance of forces, a symphony of physics if you will, that keeps our train chugging along its tracks. It's the perfect blend of physics and engineering that makes this possible. But what happens when things go wrong? Let's talk about safety measures. When it comes to rail transport, safety is paramount. One of the key safety measures in place is strict adherence to speed limits. Just as cars have speed limits on the road, trains too have maximum speeds they must not exceed. This is crucial because if a train moves too fast, the risk of derailment increases. Speed limits are carefully calculated based on various factors, like the weight of the train, the curvature of the track, and the condition of the rails. By adhering to these limits, the trains ensure they move at a pace that's safe for both the passengers and the railway infrastructure. Next, we have track maintenance, which is the unsung hero of railway safety. The tracks are the foundation of the entire railway system, and keeping them in top shape is a non-negotiable safety measure. Regular inspections are conducted to check for any defects, such as cracks, corrosion, or wear and tear. Any identified issues are promptly addressed to prevent any potential derailment or other accidents. This meticulous attention to detail helps ensure the train wheels and the tracks always interact as they should. Last, but definitely not least, we have the automatic brake systems. These are designed to apply the brakes whenever a train exceeds the speed limit or encounters a problem. Modern trains are equipped with advanced detection systems that can identify potential issues and automatically apply the brakes to prevent any accidents. This is a crucial safety measure that acts as a fail-safe in case other systems fail or human error occurs. So, while the magic of train movement is indeed fascinating, it's the rigorous safety measures that make it possible for trains to move millions of people and tons of cargo every day without sliding off the tracks. These measures, from speed limits to track maintenance and automatic brake systems, all contribute to the overall stability and safety of the train. These safety measures ensure that even when there are issues, the train stays on track. So, there you have it. The mystery of how a train moves without sliding off, solved. We've taken a fascinating journey together, exploring the intriguing world of railway systems and the magic that keeps these magnificent machines on track. We kicked off our exploration with the geometry of train tracks. We learned that the subtle yet precise design of the tracks, with their slightly angled rails and calculated spacing, plays a key role in ensuring a train's stability and smooth movement. Next, we delved into the wheels of the train, which, unlike what one might initially imagine, aren't exactly round. Their conical shape, with the smaller diameter towards the inside of the track, works hand in hand with the track geometry to keep the train from derailing. Then we tackled the physics behind it all. We unveiled the invisible forces at work, like friction and gravity, that cooperate to keep the train on its course. We also explored the concept of the hunting oscillation, a natural phenomenon that ensures the train follows the track. Finally, we talked about the safety measures in place. From automatic brake systems to track inspection routines, these measures ensure our journeys are safe and sound. Next time you see a train smoothly gliding along its tracks, you'll know exactly what's going on behind the scenes. Thanks for joining us on this journey of discovery.